All right, guys, welcome to 4.2 reflections. Hopefully, 4.1 with the translations went okay. So today is going to be reflections. This is just going to be another type of translation that we did the other day. So we saw transformations. That's a whole as a goal. So your transformations were translations, which you saw in 4.1. And today you're going to see reflections. You're going to see rotations later on. So today we're going to talk about what is a reflection. Okay. So I got some stuff written down here. Go ahead and pause your video, write the stuff down. This is some good stuff. I'll explain it here in a minute. So reflection is a transformation, okay, once again, that uses a line-like mirror to reflect a figure. The mirror line is called the line of reflection, okay? So it says a reflection in a line M maps every point P in the plane to a point P prime. So you're going to have this right here, and this will be our pre-image. And what's going to happen is that we're going to reflect it over to that side. It's going to be the same distance from our reflection line. This is going to be your reflection line. You might say, Mr. Trapp, what is my reflection line? Well, your reflection line is going to change. Sometimes it could be the x-axis. Sometimes it could be the y-axis. Sometimes it could be x equals a number or y equals a number or the line y equals x. It's going to change. You're going to see a bunch of examples here in a minute. Okay. So it does say right down here that P is not on the line M. Then M is the perpendicular bisector. Now, this is something that we have not talked about. But a perpendicular bisector means it is the same distance from the line and it makes a right angle, which means that it's the shortest distance. So that's the shortest distance from each one. So whatever distance P is to that line, so is P prime to that line. Okay. Now, what happens if it's actually on the line? Okay. And that's what we have right here is that P is actually on the line M. So it really doesn't change much else except that it kind of looks really big just like that. Okay, so it's going to be the same thing. All right, so sorry about that. We're going to jump to our next page, our first example. So what you're going to see in our first example is going to be the following. Okay, so here's a question. Once again, pause your video, go and write this down because this is going to be important. Okay, so the first question says graph triangle ABC with vertices 1, 3, B is 5, 2, C is 2, 1, and its image after reflection described. So I have two problems using the same one. The first problem looks just like this. Okay, so hold on, make sure I get this right. This is kind of cool, isn't it? I may not use it a whole lot, but that's what it looks like. It's kind of cool. Anyway, so if I can get off this. So once I have this right here, we want to graph this right here. Try to click on it. There we go. So once we have this right here, we want to reflect it over this line x equals -1. Okay. So what you want to do is you want to graph each of these points, and then we're going to graph this line x equals -1. Now what you're going to see is I'm going to go ahead and just give you the solution right here, and I'm going to walk through what it is. So what you see right here is that this part right here, okay, this guy over here is what our pre-image was. Okay, that means that's where we're starting. Now we want to reflect over this line x equals -1. You need to remember that x equals -1 is going to be a vertical line. If it were y equals, it'd be a horizontal line. So you have to make sure you understand, you remember some of your algebra skills like that. If not, you need to make sure you have resources available, have this available when you do your homework. I'm going to tell you, you have a problem like this on your homework for Wednesday. You also have one on your quiz on Thursday, and there'll be one like this on Friday for your bigger quiz. Okay, so here it is. This is our pre-image. This is our reflecting line. Okay, so we want to reflect everything from here on over. So every point A goes A prime. So if you notice here, what you need to do is that once you have this graphed and then graph this line, count up. What is this distance from A to that line? Well, it looks like it's going to be 1, 2, which means that this distance will also be 2 points. So that's going to be 2. So would that be 2? If you notice, the y value is not going to change, how high it is. So that's not going to change because when we reflect it, it's just kind of begin to switch. If I had like a pole and I had a thing on one side and I twist it around, it's going to be the same distance because that's how much it is. So A goes A prime. B, if we count up from this line, it'd be 1, 1, 2, 3, 4, 5, 6. So I'd count from this line and go 1, 2, 3, 4, 5, 6. C would be the same way. I could count 1, 2, 3. C would be 1, 2, 3 right there. Okay. The Y values do not change for this if it is a vertical line like we do right here. If it's a horizontal line, it's going to be a little bit different. So our next example looks like the following. Now, x equals -1 was a vertical line. Y equals 3 is going to be a horizontal line. I'm going to move my crazy picture up there. Now, look what happens here. So now what you're going to see is going to be the following. We use a different color, have a little bit of purple action. Make it a little bit easier to see. So your original, which is your pre-image, is this guy right there. This is where you're going to end up, which is your image, okay? This right here is your line of reflection, which is y equals 3. All you would have to do is graph y equals 3 is go 1, 2, 3 up on the line, y equals 3. Just like over here, x equals -1 is 1 on the -1 axis. Sorry, -1 on the x-axis. Go up and down. So if you notice, the A right there is going to be the same. A is on the line, which means it does not change. So A and A prime are going to be the same value. That's okay. That can happen. Now, if I go to B, I want to count how many units is B away from this line. It's 1 unit, which means I go 1 more unit that way. Now, on these, the Y's are what's changing and the X does not. Notice over here, on this problem, we had X equals. The X changed, but the Y did not. Here we have Y equals, which means the Y changes, but the X does not. Okay? So my B and B prime, then I have my C. So I'm going to count from my line. I'm going to have 1, 2, which means that C prime would be 1, 2 units away. This is what reflection looks like. This is what happens when we have reflecting over lines. We have a vertical line over here, and we have a horizontal line over here. Very important that you understand what those two things mean. If you don't, you're going to make some mistakes. Okay? I'm going to go and erase my board, and we will get on to our next screen. All right, example number 2. Now, once again, write this down. You're going to want to graph these as you go. These are all great examples for you guys to have down. So for this one right here, it says graph AB. So the last question said was to graph a full triangle. On this one, we're not going to graph a triangle, but all we're going to do is graph a segment. So point A to point B, that's all we're going to graph. They give you the starting point and the end point. So they say they want you to graph this and its image, which means the image is what we're going to have to find after the reflection. Like, whoa, what is this? Y equals X. I'm going to show you. You're going to see in our picture next. So the picture actually looks like this. So let's go ahead and use a color here. How about we'll use the purple again. So notice right here, 3, -1 is this guy right here. And then we have 3, 2, which is going to be this guy. So we have this little line segment right here, AB. And then we have this guy right here. This is your reflection line. How do we make Y equals X? Well, here it is. You can make a little table, or you can just go ahead and choose whatever values you want for X. So tell me a number for X. How about 1? So if X is 1, that means Y is 1. If X is 2, that means Y is going to be 2. If X is a negative, the Y will be negative. Everything's going to be the same. So the line Y equals X is actually what we call a parent function. It is the most basic function of a linear function that's out there. Y equals X means it has a slope of 1, a y-intercept of 0, nothing too crazy. Okay? So the bottom line is that we want to be able to take this guy right here, this line segment, and we want to reflect it over here. Okay? Now, this is a little bit different than the last one that we had, because before we can make a perpendicular. Can we make a perpendicular with this? We cannot. So that leads into me, the magic statement I'm going to tell you is this right here. I want you guys to switch the X and the Y. So check this out. If A was 3, -1, that means A prime is going to be -1, 3. So let's take a look. -1, 3, there she is right there. If B were 3, 2, all I got to do for B prime is to switch the X and the Y like this. We can double check. 1, 2, 1, 2, 3. So if you have this right here, you want to switch the X and Y. Depends on how many points there are. On our problem right here, we had 2. If we had a triangle, it'd be 3. Quadrilateral would be 4, and so forth. Okay? So once again, first time we saw y equals 1 and x equals 1 and some numbers like that, you had to kind of look at the graph and walk. On this problem, you don't even need the graph. If it says y equals x, we switch the x and the y. Okay? Next, right here. So these are 4 incredible, important rules. Now, what this does not have is the x equals 1 or x equals number and y equals number. But what we have here is what happens when we reflect over the x-axis. What happens when we reflect over the x-axis is that every b will change signs. The a stays how it is, but the b changes signs. If it's a y-axis, the a changes signs, but the b stays the same. Okay? For a line y equals x, we just talked about it. Look what happens. We're going to switch the x and the y. And then we have this one right here, y equals negative x. So it's a little bit different. So it's just like the one above it, except now not only do we switch the x and the y, we are going to take the opposite sign and have it. These 4 guys right here, very critical. Have these down with your homework. They're going to help you out a lot. Trust me. I'm not just lying to you. Okay? Racist. Line of symmetry. So this is our last little part. Not going to be too crazy. This is one of those that you can kind of look at. Not be a whole lot of math that you have to do. So line of symmetry is when the figure can be mapped onto itself by a reflection in a line. Figures can have more than one line of symmetry. Okay, so line of symmetry is when figures can be mapped onto itself. And what's going to happen here is that we're going to see some different objects as we go. All right, so how many lines of symmetry does each hexagon have? So hexagon means we should have a 6-sided figure. So I look at this 1, 2, 3, 4, 5, 6. So I have a 6-sided figure right here. And I want to decide how many lines of symmetry. So lines of symmetry are what cuts it exactly in half. And you can flip it, you can fold it on top of each other. So as I look right here, what you're going to see is that we can actually have 2 sets of line symmetry. If I cut it right down the middle, like we did right here, and we fold it onto itself, would we get exactly the same thing? We would. The same idea, if we went straight down the middle like that, that would also be folded on top of each other to give the exact same picture. It's actually called an isometry. Okay? Go to my next example. Part B, 1, 2, 3, 4, 5, 6. We still have a hexagon. So with this one, what we're going to do is we're going to go ahead and decide what are our lines of symmetry. Now, you're going to see the answer in a second, but if we draw a line just like this and fold it on top, would we get the same thing? Yeah, there's 1. What about if we went left or right? Yeah, if we fold it, it'd be the same thing. So we have 2, right? Are we done? We are not. Anytime you have an object like this, you have to make sure you look at the other corners. That'd be 3. Oops, not a very good drawing, but that would be 4. Okay? So let's go see, what does our problem say we have? Our problem has a lot more than that. So what happens here is that we also have the lines that go through here. And the reason why this happens like this and the other one says that is that this is a regular hexagon, which means all the sides are the same. What does this mean? This means that you should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, actually, just 6. 1, 2, 3, 4, 5, 6 lines of symmetry. Okay? Because the lines of symmetry, once you cut it in half, can you fold it on top of itself? In this case, yes, you can. And then we get to our last one. This is still a hexagon. So I'm going to have 1, 2, 3, 4, 5, 6 sides. Can I draw it straight down right here? So if I drew a line straight down like this, would it give you the same thing? It would not. What about diagonal? Nope. What about horizontal? Yes, it would. If I flip this down onto itself, you would see that you're going to have one thing of reflection. Okay? So we have one more quick question. I have an example for you guys to do. I forgot about this one. So on this question, it says, how many lines of symmetry does each triangle have? Okay? Or does this triangle have? So as I look at this, what I want you guys to recognize is that a triangle Can we slice it down the middle and get the exact same thing? We sure can. So if I drew this down here and I took this side and put it over there, would it be the same thing? Sure would. So that means we have 1. Now, this was an equilateral / equal angular triangle. If I draw this right here, oops, very bad drawing, but if I'm going through the middle, yes, I would also have 1. I have another one over there. Okay, so that means I have 1, 2, 3 lines of symmetry that the triangle has. If it were a different type of triangle, it may not have 3. This one has 3 because it is an equilateral triangle. Not every triangle. Now, every equilateral triangle has 3, but not every triangle does. Okay. In fact, you see some triangles that have none. A lot of them will have none. All right. So that was my last example. If you have any questions, please let me know. I'll be more than happy to give you guys a hand anytime. Miss you. Hopefully, you guys have had a good break so far when it comes to Thanksgiving and everything. Please give me a shout if anything. Have a great day, and we'll talk to you later.